Hi, this is a video for compiler design. This is COMP442 and 6421. This is for week 3. In this video, we're going to see an introduction to syntax analysis. Share. So in this video, well, we're going to start explaining what is parsing. We're going to cover in the course different parsing techniques. I'm going to start with explaining what is parsing. Then I'm going to go to predictive parsing in this particular video, but we're going to see other parsing techniques later on. We're going to spend 3 or 4 lectures talking about different aspects of parsing. Here I'm going to explain what is the notion of a derivation, which is the central concept of what is parsing, which is to build a derivation. Then we're going to see also that very often when you build a parser, you have to, well, it's based on a grammar, and very often you would have, especially if you're doing top-down predictive parsing, you have to transform your grammar. Sometimes there's a problem with your grammar, depending on what the parsing techniques you are using. You may have to transform your grammar. So that's one of the things that we will have to do in the project, so that I'm going to explain that today. Then I'm going to explain what the parsing methods that you will have to use in the project, which is one of the predictive parsing techniques, either recursive descent or top-down table-driven predictive parsing. In order to explain that, you also need to understand what is the notion of first and follow sets. In this video, I'm just going to introduce what is the notion of first and follow sets, but I'm not going to explain how to produce them, which is going to be in the next video. So what is syntactical analysis? So syntactical analysis essentially is about parsing the token sequence to identify what is the syntactical structure of the program that this sequence of tokens is representing. So you basically want to take the sequence of tokens, make some kind of analysis, and figure out if the sequence of tokens is syntactically valid according to the definition of the language. So what is the output? So you're taking an input, a sequence of tokens. What is the output? Very often the output would be an abstract syntax tree. So an intermediate representation, which is most often an abstract syntax tree. So the parser, or the syntactical analyzer would take a sequence of tokens and then generate an abstract syntax tree. Then this abstract syntax tree can be traversed essentially and processed further by the following phases of the compiler. You don't necessarily need to have an intermediate representation, but in the project, that's what we are going to do. So you're going to have to build an abstract syntax tree as the parser is actually operating. We'll see that in an upcoming lecture, not today, or not in this video. So how is this, well, what kind of grammar, what is a grammar? So a kind of grammar that we are utilizing is what is called a context-free grammar. So, so that's essentially a grammar that recursively defines the syntactical structures, the individual structures that are components essentially of the language, that assembles them together and specifies in what order they actually, how can they be combined, and what's the valid order in which they can be combined. Okay. So, and the bottommost components of this grammar is the actual tokens. So essentially, it's telling you in what order tokens can be combined, so that the sequence of tokens actually forms a valid program. So after you have the abstract syntax tree, then you can analyze this tree, you can augment the tree, and you can transform the tree by the following phases of the compiler. If you don't have an abstract syntax tree as an intermediate representation, it's possible to do the processing, but it becomes more intricate because everything now has to be embedded inside of the parsing method that you are using, the parsing algorithm that you are implementing. It's possible to do that, but it's much more flexible to use an intermediate representation. There are, so parsers, you can write them by hand. That's what I'm going to be asking you to do for the project. But in real life, what you would be doing is use what is called a parser generator. So a parser generator is essentially a computer program that receives an input, a grammar that is written in some form of EBNF, as we will see later, and reads this grammar and somehow is able to analyze this grammar and then generate the parser that corresponds to this grammar. So there are, yes, tools that are able to do that. As we will see how you can actually build a parser, it will also show to you how a parser generator is actually working. Okay, so again, I'm not allowing you to use a parser generator in this course because the objective of the course is to figure out how it works internally and being able to do it yourself. Okay. If you'd be, if I'd be allowing you to use a parser generator, then you'd be just basically somebody who knows how to use tools. This course is more about learning how it works, how these tools actually work. What are the roles of the syntactical analyzer? Of course, it is about analyzing the structure and then of the program that you provided to provide to it an input. So analyzing what are the declarations, the definitions, the statements, the expressions, down to the actual components and eventually a sequence of tokens that were provided in input. Okay. So it will check for and report and recover also from syntax errors. As you know, as a programmer, very frequently when you write a program, there are errors in your program. One of the very important jobs of the compiler is to give you hopefully meaningful error messages so as to guide you as to what are the problems in the program that you wrote. So yes, the main job of the compiler is to generate the executable for a valid program. But if it's not valid, it's as useful as generating the output for a correct program. It is also extremely useful to give meaningful error messages for invalid programs and be able to continue parsing even if there are errors in the program. Okay, we'll see that later on, and again, not in this video. Most often, the syntactical analyzer would actually drive the front end's execution. So the driver of the front end is the parser. You start the parser. For example, the parser would start executing, and as it's executing, would actually ask the lexical analyzer to give it the next token. And as it's proceeding, would actually generate the abstract syntax tree. So the syntax of the parser is actually the kind of the heart of the whole compiler. It could even be, if you're using what is called syntax-directed translation, that the parser is the only thing that's driving the entire process. In our case, we're going to generate this abstract syntax tree, which is going to create some kind of intermediate representation. And then later on, other phases would actually take this tree and process the tree. So a little bit of history. So how did it come to be? So essentially, this is based on the notion of generative grammar. This notion was actually invented by Noam Chomsky. So you might know this person as being some activist. Yes, he's an activist, but he is also a person who invented this notion of generative grammar. It's actually a linguist. So essentially what a linguist is a person who is a mathematician who's trying to represent languages and how to process and identify and analyze languages, okay, in the form of mathematical concepts. So he invented this notion of a generative grammar, which is essentially that you can define a language using a set of what is called predictions. And then by using these predictions, you can generate sentences. Okay. So that's the notion of generative grammar. So he actually invented this notion in the 1950s. So you see that's even, you might say, before compilers started existing. And of course, when people were designing the first compilers, and they were looking as in different places to figure out how they can actually build a compiler. And a computer being some kind of calculator, and they basically were using math. Linguists were mathematicians. They were also interested in the computers. So of course, and these two groups of people met, and then that's how the computer scientists started using Chomsky's theory for building compilers. So what is parsing doing? It's consists in determining the way in which sentences can be constructed using predictions. It's essentially building some kind of proof, which is called a derivation, that proves that from the what's called the starting symbol of the grammar, you can actually generate a certain sentence. So there are many different parsing algorithms which are all doing the same concept of building a derivation, which is basically what is a parser is some kind of theorem prover. Okay? So you give it a sequence of tokens, it has some rules, and then it tries to somehow prove that these rules can be used in a certain sequence to generate the sequence of tokens that you have in input. Okay, so it's a kind of a proof system, automated proof system. So there are different kinds of algorithms that were designed, mostly in the 1960s for the parsing problem. We'll see some of them in the course. I'm not going to cover all of them. We'll see some of the, first of all, top-down methods, and then some of the bottom-up methods later on, but not all of them. There are also other contributors. For example, Donald Knuth is very famous for having, I might say, popularized or explained clearly the parsing algorithms. So he's the author of the books, series of books, The Art of Computer Programming. And in these books, he actually presents very clearly these algorithms and how you can actually turn them into computer programs. This series of books is a magnificent piece of work. So that's Donald Knuth has also done many other things, but that's one of the things that he's very famous for, to, somehow make this theory behind parsing, to make it translated into algorithms which are easy to implement. Sometimes people come up with mathematical theories, but it's not that clear how to implement them. So Donald Knuth makes sure that these these two realities actually met in his book, or his series of books. Okay, so here's an example. So here the example is about English language, and the English grammar, if you want, a grammar for the English language. So you have a sentence can be defined as a noun phrase followed by a verb phrase. This is only one of the possible kinds of sentences in the English language. There are many of them. That's one of the simple ones. Then you can define a noun phrase as an article followed by a noun. And then these are basically atomic elements. So in terms of a programming language, these would be tokens that you identify. Okay. Then a verb phrase can be defined as a verb followed by a noun phrase. Okay. So you see that they are all using one another. These definitions are using one another, so on. So the idea is that you want somehow to let's say you have a sequence of tokens in input or sequence of words in input in this case. Let's say the sentence is the dog gnawed the bone. And then you want to prove if this sentence is a valid English sentence. Okay. So essentially what you want to do is start with the top symbol of this grammar, of this simple grammar, which is sentence. And then you want to somehow build a tree that is composed using these rules here. And that is actually eventually creating a tree that's creating a tree whose leaves are all the sequence of words that you find in this sentence. So a sentence is a noun phrase followed by a verb phrase. The is an article, dog is a noun. So noun phrase is an article followed by a noun. This is the dog is a valid noun phrase. So that's one part of the proof. Then you have that sentence is a noun phrase followed by a verb phrase. Then a verb phrase is a verb, which gnawed is a verb. That's another part of the proof. And then a verb phrase is a verb followed by a noun phrase. And a noun phrase must be an article followed by a noun, which the is an article and bone is a noun. So this tree here that has been built using these rules here is a proof that the dog gnawed the bone is a valid sentence. Now this is using a tree, but you can also build that as a sequence of transformations, as I will explain a little bit later. So there is also this notion of syntax and semantics, which is often not clear to some people. So let's clarify this a bit for now. We'll see that much later also. So a syntax defines how valid sentences are formed. So syntax is about form. It's about the structure, the sequence in which tokens are appearing, okay, which can be translated into subtrees and so on. Okay, so it's about structure. Syntax is about structure. Whereas semantics is about defining the meaning of valid sentences. Okay. So semantics is about meaning. So you can have a tree that defines that a proof that a certain sentence is syntactically valid, but the sentence can be syntactically valid and be semantically invalid. Okay. So for example, you could have a sentence like this, which is actually a syntactically valid sentence. For example, the bone walked the dog. So this is, according to the rules we saw before, this is a valid English sentence. But of course, as a human, if you try to figure out a meaning to this, then you probably come to the conclusion that this is not, this sentence cannot have a meaning. It's meaningless unless somebody's nickname is the bone and this person is walking their dog. Okay, so you see, this is where the English language and a programming language diverge from one another. When you're talking about a programming language, every word you use should have, one and only one meaning. Okay. So that's what we, parsing and processing human language and parsing and processing computer languages, it's two different things. Here, we're talking about processing computer languages. it is actually a very difficult problem to actually try to find the meaning of any syntactically valid English sentence. This is a good example. Okay. Somebody might write this sentence in their poem, in which case they would argue that it actually does have a meaning if you use your own imagination. Okay. But there's no such thing as the compiler using their imagination. Okay. Things have to be very exact and have one and only one possible meaning to a valid program. So spoken languages may have ambiguous meanings. For example, bone might have actually different meanings depending on who you are. You might know somebody whose nickname is Bone, but that's different from bone being, bone in a living person. And then programming languages must be non-ambiguous. That's taken for granted that you don't have ambiguity in a programming language. If you have a valid program, it can have one and only one meaning. As you translate it, it's going to have one possible translation. Okay. Eventually, we're going to define the semantics or the meaning of a program, and we're going to actually generate an executable program that implements this one and only one meaning for the program. So we're going to give one meaning to the program, which is going to be encoded in the executable. Now, what is a grammar? So here we go and defining what's the notion of a grammar so that we can use it. So a grammar is a quadruple TNSR. T is a final set of terminal symbols. Terminal symbols are essentially your tokens that you have identified in the lexical analyzer. N is a finite set of non-terminal symbols, which are some kind of abstract concept that is some kind of abstract component in the language. For example, if you have an object-oriented language, programming language, for example, the notion of a class is some kind of abstract concept that can be composed using a sequence of tokens, or a statement, or a variable declaration. These are all abstract concepts that can be represented by a lot of different sequences of tokens. Okay. So that's what is a non-terminal symbol. It's a symbol that represents an abstract concept that is composed by other, that is a composition of other concepts. S is a unique starting symbol that is one of the non-terminal symbols. So this is eventually what's going to be at the top of your tree. Okay, it's the starting point of the whole proof that you are building. And there should be one and only one starting symbol in any grammar. Then R is a finite set of productions. So for example, in my example before, these are my productions. Okay, here I have 3 productions. So what is a production? What's the definition for it? So essentially you're taking alpha and transforming it into a beta. Now, what is alpha and beta? It's a sequence of terminals or non-terminals. Now here I define here, there's 2 different possibilities of terminals and non-terminals. Or sequences, sorry. So if it's a sequence of terminals and non-terminals, it's called a sentential form. So for example, a sentential form can be the dog, verb, the bone. Okay, so here you have some terminal symbols and then a non-terminal and then some other terminal symbols. So any sequence of terminal or non-terminal is called a sentential form. So essentially a finite set, production is something that a rule that defines that you can actually transform a sentential form into another sentential form. Okay. So that's the most general definition of what is a production. for a grammar, but if you restrict yourself to what is called context-free grammars, which are the ones that we're using in programming languages, processing, and the parsing problem, we are using context-free grammars. In context-free grammars, the rules are of the form A is transformed into beta, where A is a non-terminal and beta is a sentential form. So you cannot have, the only thing you can have on this side of the arrow here of the transformation is a unique non-terminal. So so a sequence of terminals and non-terminals is called a sentential form, as I said before. If you restrict yourself to only terminals, then a sequence of terminals is called a sentence. For example, the dog gnawed the bone, or gnawed bone the are sentences. So note that a sentence doesn't mean that it's a valid sentence. A sentence is just a sequence of words or tokens or terminal symbols. So we're going to use these concepts, of course, extensively as we go further. Now, we need to have a way to actually express a grammar so that it can actually be processed somehow by a computer. So this is an abstract mathematical definition of what is a grammar. Now, how can you represent it? For example, how can you store a grammar in a file? So there was, of course, this problem very early in the design of compilers. So the most common solution for this is what is called the Backus-Naur form. So that was invented by John Backus and Peter Naur. John Backus was the main person responsible for the designer, the design of some of the first Fortran compilers. Essentially, some of the first compilers that were ever designed. So they somehow had to find a way to store the grammar into a file. So they figured out some kind of meta language to express grammar. And then Peter Naur, where eventually the original language done by John Backus was augmented by Peter Naur, which was one of the designers of the ALGOL programming language family that is the ancestor of most of the procedural programming languages that as we know nowadays. ALGOL was a very important milestone in the development of programming languages. So what is this language? Essentially, the Backus-Naur form is a language that you use to express grammars that themselves express a language. Okay? So that's why it's called a meta language. It's a language that you use to express languages. So what is this language? So non-terminals are placed in angle brackets, and the symbol : equal is used instead of an arrow, because you want to store this in a file. Arrow is not a very typical character that you can put in a file, so they decided to use this notation here: : equal. Vertical bar can be used to signify alternatives. So if you have, for example, A is defined by a sentential form or another sentential form, then you would use a vertical bar. If you would have repetition, then you would use curly braces. So you would have a sentential form encased in curly braces that specifies that you can have any number of consecutive occurrences of this sentential form. If you have optionality, so for example, a sentential form is optional in a sequence, then you would put this sentential form in square brackets. So this is something that is used very extensively. So, for example, if you want to describe a subset of the type declarations in the language Pascal, then you would do something like this. So you see that these are your non-terminal symbols in angle brackets. And then these are your terminal symbols. And then you have here optionality with the square brackets. And then you have here the repetition using the squiggly brackets. And some examples of type declarations that are valid according to this grammar here would be these that you have here. Okay. So this grammar here can be used to generate any of these sequences of tokens that you see here. So that's going to be one of the examples I'm going to use very extensively. So you're going to see this example being refined and used in various lectures, upcoming lectures. So let's say I want to define a grammar to define expressions in a programming language. So my grammar is a TNSR, as I described before. My set of terminal symbols are those ones here. And my set of non-terminal symbols is a singleton, which is E. So you see that this is very simple in this way, but we will soon see that this is creating some problems by having only one non-terminal symbol. It can work, and it actually makes the grammar quite simple, but sometimes the grammar being simple is actually getting in the way of some other properties that are necessary to have, as we shall uncover in this lecture. Then my starting symbol, of course, there must be one and only one starting symbol. My set N is a singleton, so of course my starting symbol is E. Then my rules, what they are is these are rules of a, as we defined earlier, the rules must be of this form here. We are talking about a context-free grammar. So what is on this side of my arrow must be a non-terminal symbol. So non-terminal, and then arrow, and then sentential form. So all my rules here are defining an expression. So an expression can be E plus E, or E minus E, or E times E, or E divided by E, or E between parentheses, or ID. Pretty standard and very easy to understand. So you should expect that we will see this grammar over and over again in the upcoming lectures. So what we want to do is, for example, we have a sequence of tokens, or in this case, a sequence of characters. Let's start with the first step, sequence of characters, A plus B between parentheses divided by A minus B between parentheses. So first, the first thing we want to do is to tokenize this sequence of characters. Then we might say that we come up with these tokens. Okay. So then what you want to do is to construct a parse tree that corresponds to this sequence of tokens. Now, what's going to happen is that the starting symbol of the grammar is going to be the root node of the tree. So for every tree that you build, it's always going to be the starting symbol at the root of the tree. Then for any internal node in the tree, meaning a node that is not a leaf node, is actually a non-terminal symbol. And any leaf of the tree is always a terminal symbol. The application of a production for a valid sentential form is a subtree. Of course, the whole tree is representing the whole sentence, but a subtree represents a subset of the sequence of the sentence that is represented by the program you're trying to parse. And of course, the valid sentence as a whole is represented by the whole tree. So then we start at the root with the starting symbol, and then we build this tree downwards by using one rule at a time. Okay. Now here I'm gonna, the first example I'm gonna, as you will see, first example I'm gonna give, I'm gonna use my own judgment, okay, to build this tree, to make the decision as to what rules I'm gonna use in what order. We're soon going to realize that a parser cannot do, a parser, of course, does not have the knowledge I have, so it cannot make these decisions that are based on knowledge. It has to be mechanical. So what first example is going to use my own knowledge, but then we're going to see very soon how it can be done mechanically somehow. So this is the sequence of tokens that we have. And what we want to do is to build a tree. So eventually we're going to build this tree here. Okay. So first you start with E at the top of the tree, which is the starting symbol. Then you try to determine what rule I'm going to first use in order to build this tree. Now, I know from my knowledge of arithmetics that I should use divide before. Okay. So now I'm going to say E is E divided by E using this rule here. Then I have this tree here, and then I have these two E's here. Then I'm going to transform these E's into other sentential forms. So I'm going to take this E here, and as I'm aiming to have this here, then I'm going to have E between parentheses that replace this one, as well as this one here. So now I'm going to have E between parentheses divided by E between parentheses. Then eventually, of course, then I have an E and an E here, which are not terminal symbols. So I'm continuing this process until all I have at the leaves of the tree is terminal symbols. That's my goal. So then I actually transform these two E's here. The first one, because here I'm aiming for a plus expression and a minus expression. So I'm going to replace this E by E plus E using this rule here. And replace this E by E minus E using this rule here. Then, of course, I'm going to use this rule here to replace all the E's by ID. So you see that this tree, if you traverse this tree, you go parenthesis ID plus ID parenthesis divided by open parenthesis ID minus ID close parenthesis. So this tree here actually is a proof that E can derive this sequence of tokens. Now, as I said, now in this process here, of doing this proof, I've used my own knowledge, human knowledge that I have about arithmetics, which you, of course, should not assume that a parser would know that as it's operating. So we have to use certain way to organize the parser so that it processes this, comes up with the same result, but in a mechanical manner. So the way to, what is the actual process that I did here, I basically built a proof. So in terms of parsing, this kind of proof is called a derivation. Okay. Derivation is essentially a proof that proves that from the starting symbol, you can actually generate a given sentence. So a derivation is essentially a sequence of transformations that you apply from the starting symbol, and then you would generate sentential forms, and then eventually you transform these sentential forms until the sentential form is composed only of terminal symbols, in which case it becomes a sentence. And if you can prove that the starting symbol can generate the sentence that you had an input, then you have successfully built a derivation that proves that this sentence that you had an input is valid according to the grammar. So each of the transformations, the individual transformations, are essentially transforming one sentential form into another sentential form. So alpha is transformed into beta, where alpha and beta are two sentential forms. Okay? And then each of the individual transformations is actually done using one of the rules raw in your set of rules R of your grammar. Okay. So you have a sentential form, you transform it into another sentential form using a certain rule in your grammar. And a derivation is essentially a sequence of such transformations that the first one is transforming the starting symbol into a sentential form. Then the sentential form is transformed into many, many steps. And then at the end, the last step is essentially what you have created is the sentence that you wanted to prove that is valid according to the grammar. Now let's see in practice what that means. So for example, I can have, the example I gave before. So essentially you start with E. So these are all your derivation steps here, as I actually define here. Okay. So your first derivation step is taking E, which is the starting symbol, and then transforming it into the sentential form E divided by E, using this rule here in your grammar. Then you can actually take this E here and then transform it into E between parentheses using this rule here. So you see here that you took E divided by E and then you transformed it into E divided by E between parentheses using this rule here to transform this E into another sentential form. So you're taking one of the non-terminals in the sentential form and you're transforming it into another sentential form. Then I might actually take this E here and then transform it into E minus E. So then I have taken this sentential form and then transformed it into this other sentential form using this rule. Then I do the same and transform this E into an ID using this rule, this E into an ID using this rule, and then this E into E between parentheses using this rule, and then this E into E plus E using this rule, E into ID, and then E into ID. And then I have proven that in the sequence of steps that E can derive this sentence that I wanted to prove that is valid according to the grammar. So this is essentially a formal proof of that this sentence is valid according to the grammar. So formally speaking here, what you're doing is that you have proven that there is a transformation, a multiple step transformation using the grammar G, that E, the starting symbol, can be transformed in multiple steps using the rules in the grammar G into this sequence of tokens or this sentence. That's the proof that you build there. Now, what is the language that this E or this grammar can actually generate? Language is the set of all sentences that can actually be generated in multiple steps by the grammar G from the starting symbol of this grammar. So the language is a set of all sentences that can be generated by this grammar. Now, there are two different, so that's only one way that you can actually do this transformation. So you see here that I have apparently arbitrarily chosen always the rightmost non-terminal symbol in my sentential form. Okay, so there, I could have chosen any one, and eventually that I would have come to hopefully to the same result. Okay. So there are, if you want to proceed more mechanically, because this is where we're going to, because a program is doing things mechanically. That's the best way to actually come up with a good result. So you can do a what is called a leftmost derivation or a rightmost derivation. So you see that what I did in the previous example, I did a rightmost derivation in the sense that I was taking always in my current sentential form, I was always taking the rightmost non-terminal, unresolved, I might say, non-terminal in the sentential form. That here, this was an E and an E and an E and so on. And then the E becomes an ID. Then I go to the next rightmost ones. One in the next rightmost one, unresolved non-terminal symbol in the sentential form. And that's how I proceed. That would be a rightmost derivation. You can also do a leftmost derivation by electing to choose always the leftmost unresolved non-terminal. So this is a choice. Okay. So there are some parsers that would do a leftmost derivation and some others that would be doing a rightmost derivation. Now, of course, which normally when you read something, you start from the left to the right. So you might say, well, it's not very intuitive to do a rightmost derivation. But what's happening is that when you do when you implement a parser that does a rightmost derivation, normally what it does, or how you should think that it proceeds, is actually it builds the same proof that is a rightmost derivation, but in reverse order. Okay. For example, it starts with the sequence of tokens and then takes the leftmost one and then resolve it first. So you see here that my arrows here are in the reverse order. So essentially, this is a proof from E onto that, but presented in a reverse order. And if I see it in reverse order, then I take the tokens as they are coming in from left to right, which is the order in which I'm reading, of course, my program. So a top-down parser would be building a leftmost derivation. And a bottom-up parser would actually be building a rightmost derivation, but in reverse order. Okay. Now, one of the things that we will soon realize, and that's what I'm going to explain here, is that often you have to transform your grammar. Okay. That's one of the biggest problems that you will have in the entire project, to actually apply transform, figure out how why the reasons why your grammar might have to be transformed, figure out especially figuring out all the places where the grammar needs to be transformed, apply a local transformation for each of these places, and then eventually transform the grammar until you figure out that it does not need to be transformed anymore. Okay. There are tools that you can use to help you doing that. But that's one of the difficult parts of the entire project. So before you start building the parser, you will have to transform your grammar. And that's what I'm explaining here. So first of all, if you have optionality and repetition in your grammar, optionality and repetition are not things that are part of a context-free grammar. Okay, so you have to remove them. So essentially, you take every optionality that you have in your BNF representation of your grammar and you transform it into rules that are according to context-free grammar. Same thing for repetition. Now, one of the things, as we'll see later in the lab, I actually built myself a tool that can automatically take a grammar that has optionality and repetition and automatically remove them. Okay. So yes, there are tools that you can use to help you, but we will soon see that there's no such tool that can actually automatically transform any grammar. Okay, that does not exist. So So then you may ask, well, why do you include optionality and repetition? Because it's a way of presenting that is easy to understand for a human, and that's what you will soon realize, that when you start transforming the grammar I will give you, it will be very well understandable for you as a human and as a programmer. You will clearly see what this language is when I'll give you the grammar of the language in EBNF. But you will soon realize that the more you apply transformation, the more it becomes something that is very tricky to understand. Okay. So all of these transformations is going to add more rules, and it's going to become less and less somehow understandable. And that's what is that one of the difficulties, is that it's going to be become more and more easy to apply a new transformation to solve a problem, and that it's going to become hard for you to figure out if you made a mistake or not. Okay. So there's also some other problems which I'm going to highlight here. So you have to spot all of these individual problems by analyzing your grammar. So for example, my tool would enable you to figure out what are the problems. Essentially, the problems are ambiguities in the grammar. So you find all the ambiguities and you apply a transformation to remove each of them until there's no more ambiguities. First, before you can even figure out ambiguities, you need to remove optionality and repetition. So if you have angle brackets and squiggly brackets in your ABNF grammar, you have to remove them, and that's the first step, because these are not part of what is a valid context-free grammar. Now, if you have a rule of this form that has the angle brackets, which specifies that this sequence x1 to xn is optional in this sentential form here, then what you do is you introduce a non-terminal n in your grammar, and you go a is alpha n beta, where n is representing this. Now, what is this? This is essentially either the sequence of tokens x1 to xn or epsilon, where epsilon, of course, is the empty sequence. Okay, you see that's pretty simple. Nevertheless, you have to mechanically go over all of these and remove them. I designed a tool that is actually doing this automatically for you, that you will have access to and explain to you in the lab. Then you may have also repetition. If you have repetition, they will be represented by the squiggly brackets here, which means that if you have a rule like this, this means you can have an alpha and then any number, including 0, of repetition of x1 to xn, then followed by beta, where of course alpha and beta are sentential forms. Then again, you introduce a non-terminal n, then you have a is, you eliminate this rule here and you replace it by a is alpha n beta. Then what is n? N is any number of times you repeat this sequence here. So n is this sequence followed by n, which is this sequence, this sequence, this sequence over and over again until you reach the n, in which case n is epsilon. Okay. So you see here that you created some rule that does a right recursion. This is a rule that uses right recursion to create a sequence. Okay. You could have done a left recursion, but we will see later that left recursions are not something you want. So you better create right recursions when you remove your repetitions. So essentially here, I'm replacing this EBNF notation that is not part of what is a valid context-free grammar, and I'm generating rules that are valid according to the definition of a context-free grammar. Now you can have what is called an ambiguous grammar. And when you have a grammar that is ambiguous, what that means is that for a valid sentence, that you can have actually more than one derivation that proves that this sentence is valid according to the grammar. For example, if you have ID plus ID times ID, and you have this grammar here, then it can actually be, if you build a derivation that proves that E can generate this, then you could actually have two different derivations that prove the same, that this sentence can be generated from E. Of course, you don't want to have that. So you want that the case is that there's one and only one derivation that can be used to prove that a sentence can be generated by the grammar. So then we need to figure out a way to change this grammar so that this ambiguity is not in the language. As a human, you would, of course, soon realize that the problem here is that this grammar does not know somehow, or does not somehow encode the fact that the times and the divided operator should have precedence over the plus and the minus operator. Okay, now that's a particular characteristic of arithmetics that you need to encode somehow in the grammar. So there are different solutions to actually solve this problem. So either you would incorporate operator precedence in the parser. There is what is called operator precedence parsing that you can implement somehow automatically, but that makes the compiler more complicated. And this is rarely done. Of course, in our case, the very definition of an arithmetic expression is that times has precedence over the multiplication operators have precedence over the addition operators. But if you want to automatically do that, then you need to have what is called operator precedence parsing that identifies the precedence in the rules and in the grammar. You can also implement backtracking. And so that will also make the compiler more complicated and also inefficient. We'll come back to that later. You may also, which is always what is most used, transform the grammar to remove the ambiguities. So eventually, what you would want to do is to actually transform this grammar here so that it actually is transformed into something like this, which introduces the notion of a term plus the notion of an expression, where a term is actually involving the multiplication operators, which then give precedence to the multiplication operators. Okay. Of course, that you would need to manually be doing that yourself. There's no predefined transformation that will allow you to do that. Another thing which can be automated is factorization. So let's say you have A, which is defined as little ab or little ac or b. So in this case, if you want to transform an A, then it's either transform into A something twice in two different ways, or A is transformed into B. So if you're aiming for A something, then you have either of these two rules that you can apply. Okay? And at this point in time, given that you only know that A is the next token, you would not be able to know which one of these two to choose. Okay? So what you can do is to actually transform this grammar by factorization, by making it so that, for example, A is AD, and then D is either B or C. So you've actually taken these two rules here and applied a factorization transformation on these two rules. This can be automated. Now, another problem, which is some kind of also ambiguity problem, is left recursion. So what we are aiming to do here is to do what is called predictive parsing. Okay, so predictive parsing, what it does is, as I hinted at before, is that it's a kind of parser that, given only one next token input, is going to be able to make a decision at every step of the way as to what right-hand side to actually use. Okay. So a predictive parser, for example, could not deal with these two rules here, because if it sees A as the next token and it's currently parsing a big A, it sees little a as the next token and it's currently parsing a big A, then it would not know which of these two right-hand sides to choose, because they all both starts with little a. Okay. So a predictive parser would not be able to deal with a grammar like this. So if you want to implement predictive parser on a grammar like this, you have to transform it into a non-ambiguous grammar. Now, a particular kind of ambiguity is when you have left recursion. Well, here it necessitates to explain that the notion of why is it an ambiguity, because essentially a left recursion is the fact that you have an ambiguity between what is called the first set and the follow set of the actual non-terminal in question. Okay. Here, essentially, this was an ambiguity on the first set between two first sets. We'll come up to first and follow sets later. All this to say that left recursion is also some kind of ambiguity, but between first and follow set. But more simply stated, left recursion is a problem, because if you are using a predictive parser, then the predictive parser, what it will do is that it will assume there's one and only one rule that can be used. If there's many of them, it would choose the first one. Okay. And then if there would be, if the right-hand side of the actual rule that it chose is actually starting with the same symbol that is on the left-hand side, then eventually it would be trying to build a tree like this that is an infinite application of this rule here. So if you have ID plus ID plus ID, then it's gonna want to generate from E this ID here. So it's going to choose this rule here, and it's going to apply, transform this E into E plus E. Then the first is going to be E in the sentential form here. So it's going to transform this E again in E plus E. Then it's going to come here again, transform an E into what? E plus E, and so on and so forth infinitely. Okay. Essentially, when you're doing predictive parsing, you cannot have left recursion, or else it would go infinitely like this. Okay. But in practice, as we will see later, what's really happening is that there is an ambiguity between the first set of E and the follow set of E if you have left recursion. So these are easy, because these are what is called immediate left recursion. You have E on the left-hand side, and then the sentential form on the right is starting with the same thing, E, same non-terminal E. These are very easy to see. However, you can also have non-immediate left recursion. For example, A is B alpha, and then B is defined as A beta. In this case, you have non-immediate left recursion. So A is transformed into B alpha, and B is transformed into A beta, and so on and so forth. And then, of course, this is only one step. Non-immediate, you can have n steps, which can, of course, the more you have steps in between, the more they are difficult to locate. So any kind of left recursion, including non-immediate left recursion, you must remove them. Very often in programming languages, you would have immediate left recursions, and non-immediate ones would be very, very rare, fortunately. Then what you want to do is to transform or eliminate these left recursions. Now, luckily, there is a way to automatically do this transformation. Now, how do you do this transformation? So let's say you have in your grammar rules that define A, okay? And some of these rules are actually left recursive. So you have A can be defined as A alpha 1 or A alpha 2 or A alpha 3. So each of these rules here suffer from left recursion. Then you can also have some other rules in the grammar that define A, but that are not left recursive, that do not start with A. So these will be these ones here. So you have to extract these from your grammar to apply the transformation. Now, what you do is you introduce a non-terminal A prime. Okay. Essentially, what you're going to do here is you're going to transform this left recursion in your grammar into a right recursion. Okay. You're not going to remove the loop. You're just going to transform this loop as being expressed using left recursion, transform it into right recursion, which is going to eliminate the problem. So you introduce this non-terminal A prime, and then you essentially remove these left recursion rules that that are undesirable, and you transform these or introduce these rules, beta 1 A prime, beta 2 A prime, beta 3 A prime. Okay. So you start with these here, and then you say my recursion is going to be on using this A prime here, but all starting with different things, the different things that you have here, which are not left recursive. Then this A prime here is what does the right recursive part, that is generating the list. So A prime is alpha 1 A prime, alpha 2 A prime, or alpha 3 A prime, or epsilon, which is making the looping stop, the recursion stop. So that's how you actually transform or eliminate the left recursion by transforming, eliminate the left recursion by transforming the left recursion into a right recursion. Now, let's say we have in our grammar, let's say this is our grammar. Okay, so E is either E plus T or E minus T or T. So you see that here I actually introduce the precedence of the operators, okay, to remove this ambiguity. Now, I remove the ambiguity, but still there is left recursion. So you see I have recursion on E, because E is E plus T or E minus T. So both of these will suffer from left recursion. I also have left recursion on T. T gives T times F, and also T gives T divided by F. These are two left recursions I also want to remove. I must remove them one after the other. This first transformation here is taking care of these left recursions. So as I said in the previous slide, so I want to isolate the rules that the rules that define the non-terminal that suffers from left recursion, which is in the first case E. So these are all the rules defining E. First, I identify the rules that suffer from left recursion, and I separate them from the rules that don't suffer from left recursion. These E plus T and E minus T are the right-hand sides that suffer from left recursion. And E gives T is the only one that does not. So in this case, if I follow my definition of the transformation, my A here is E. And then A is E here, and then alpha 1 is plus T, and then alpha 2 is minus T. So remember that alpha and beta are sentential forms. Okay. And what is my beta 1? It's my t here. Okay. Then I introduce a new non-terminal symbol, a prime. So a is e, so a prime is e prime. Then what I do is I eliminate these left recursive rules and I replace them by beta 1 a prime. What is beta 1? Beta 1 is t. So I replace these rules here by a gives beta 1 a prime or e gives t e prime. So that's the first part of the transformation. Then I introduce my e prime, which is doing the right recursion. Now I introduce a prime gives epsilon or a prime, alpha 1 a prime or alpha 2 a prime. Alpha 1 is plus t, alpha 2 is minus t. So I have e prime gives epsilon or alpha 1, which is plus t, and then a prime, which is e prime. So plus t, e prime. And then alpha 2 is minus t, and then a prime is e prime. I have applied the transformation. So my transform grammar with having the e left recursion remove is this grammar here, where the e does not anymore suffer from left recursion. Essentially, I have replaced the left recursion on e by a right recursion. That's how you apply the transformation to remove left recursion. Then you can do exactly the same for removing a left recursion for t. I'm not going to go into this example here, but eventually you can remove it by exactly the same procedure, and you come up with these two rules here. Now you have a grammar that does not have any left recursion. So one of the things you'll have to do in assignment number 2 is to locate the left recursions and then transform them into right recursions. The tool that I have actually helps you do that also. Now, what if you have non-recursive ambiguity? Because as I said, left recursion might seem that it's different from ambiguity. It's a special kind of ambiguity where you have ambiguity between first and follow set. If you have non-recursive ambiguity or ambiguity between first sets, then you would have rules of this kind. So A is defined as alpha beta 1 or alpha beta 2 or alpha beta 3. So you have 3 different rules here that all starts with the same thing. So the idea of a predictive parser is that when it's trying to parse an A, then the first thing that it sees here in each of the choices that it has should be allowing the parser to make a decision. So it should not, you should not have 2 rules, 2 right-hand sides that start with the same symbol. Okay. So you want to remove these ambiguity here on alpha. How do you do that? You basically do a factorization. So let's say you have rules of this form here, which all suffer from an ambiguity. So you extract them. So you extract all the rules that suffer from an ambiguity in your grammar. You introduce a new non-terminal a prime, if the non-terminal is a. And then you eliminate these rules, and then you create a rule which is now alpha a prime, which is the alpha that you had in common between each of the sentential forms as the right-hand sides of your ambiguous rules. And you create another rule, which is defining a set of rules that defines a prime, which is a prime is either beta 1, beta 2, or beta 3. So you still have alpha followed by either beta 1, beta 2, beta 3. So you see the factorization in your rules. And then you find every non-recursive ambiguity grammar, you apply this transformation for each of them, and then you've removed ambiguities. So that's what you're going to have to do as the first step of your assignment number 2. Going to give you grammar in EBNF. You're going to have to remove the repetition and optionality, figure out where are the left recursions and the ambiguities, and remove them all one after the other, transforming your grammar. Now here I'm going to be talking a little bit more about, in detail, about predictive parsing. What's the nature of predictive parsing? So predictive parsing, as I said, what you want to achieve is that the parser actually knows what's the next token in input, and then knows that it's currently parsing a certain non-terminal, and then would basically look at all the right-hand sides that are possible, and would want, from the knowledge that the next token in input is a certain terminal symbol, and would make a decision as to which of the right-hand sides that define this non-terminal symbol that it's currently parsing, to make the decision between which right-hand side to use, which rule to use. So that's what is a predictive parser. Now it's possible that you could design a parser that may be able to deal with ambiguity, but then it would need to have backtracking. So it may, if it has two different choices, two different alternatives, then it may choose the first one, try to build a derivation used in this direction. And if it can't, then we'd backtrack back to the last arbitrary choice that the parser made, and then make the next choice, and then try it, and so on. And then after all the permutation of arbitrary choices are made, hopefully one of the cases would actually resolve positively. Okay. So you see that eventually you might have to do a lot of, but the more you have ambiguities in your grammar, the more you'd be spending time doing some backtracking, which is of course very inefficient. There is some parsers that actually work in this way. The advantage of having a parser like this is that you would not have to remove the ambiguities prior to actually implement the compiler or the parser. So it's possible that it works, but it leads to inefficient parsing. Let's see an example here. So here we have S is a starting symbol, is EE. Or BAC or BAE, where the capital letters are non-terminal symbols and the small letters are terminal symbols. Then A is either defined as D or CA. So you see here that you have an ambiguity on the small b here when you start. Okay. So I'm going to show here that it's possible to actually do a proof, derivation of this by using backtracking. So let's say you're seeking for BCDE, you're trying to prove that BCDE can be generated from the starting symbol S. Okay. So I start from S, and then I know that B is the first thing that I'm looking for. So S, well, you won't use this because it doesn't start with B. Here you have two choices. It's either BAC or BAE. So both of these rules are a possibility at this point. So the assumption is that I can only make my decision considering the only token I have, the next token I have. I cannot look and make a decision according to the next and the next and the next token. I only make decision with only one next token I have, which is B. So then I arbitrarily choose this one here, the first one. So I transform S into BAC using this rule here. Here I put a marker because here I made an arbitrary decision. Then what's going to happen is that if I come into a failure of building successful derivation, then I will undo all the transformations I made until I reach a decision point, an arbitrary decision point, which was noted using the dot here. So transform S into BAC. Then I want to transform the A into what? So now I have successfully parsed a B. So I'm looking for C. So here I have C here. So I'm going to transform this A into CA. Now I've successfully parsed the C. Now I want to find an A that starts with a D. So I have A gives D here. So I transform this A into D using this rule here. But then after successfully parsing the D, I have the next token is E, and what I have is C, which leads me to say this is an error. This is not a successful parse. However, I'm using a brute force or backtracking parser here. So as soon as I see error, then I backtrack and I undo all my steps until I reach the last decision point that I had. So I undo all of these here and make a new decision, which is taking BAE. So S is BAE, then A is transfer. So the B is successfully parsed. The next thing I'm looking is for C. So I'm looking for a rule that transforms A into something that starts with C. So CA. Transform the A into CA. Then I successfully parse the C. I'm looking for an A, a rule that generates something that starts with D. So A gives D is allowing me to proceed further by having A transforms into a D. Then I am looking for E, and that's actually what I have, which is success. So now you see that I have successfully proven that S can generate BCDE. But I had to actually undo these 3 steps here. Okay. So this is possible. You can implement a parser that would do exactly that, but it's going to be inefficient. So the more you have ambiguities in your grammar, the more it's going to spend time undoing or backtracking. Okay. So it's even possible that as it's trying to parse, that on average, it's going to spend more time going back than going forward, which is, of course, something you don't want. So it's both tricky to implement because you need to undo things. For example, and as you parse, for example, you want to build your abstract syntax tree. So not only you would be, when you undo your steps, not only you have to undo the steps, but also that means if you had built an abstract syntax tree for every step of the way, then you would have to undo the generation of your abstract syntax tree. If you had, for example, I have a compiler that generates code as it parses, then you would have to remove the code that you've built using every of the steps that you want to backtrack from. So all this to say, it creates all kinds of problems. It is possible to do that, but generally speaking, you don't want to do that. There's also some techniques that were invented that is using some kind of caching techniques to somehow reduce the, to make it more efficient, okay, by reusing some of the previously built subtrees. So that makes it more efficient, but that doesn't solve the problem of undoing and so on. So the restriction about predictive parsing is that the parser must always be able to determine which of the right-hand sides to follow, because it's now parsing a certain non-terminal, and every non-terminal has n number of right-hand sides that define it. So it wants to be able to choose the correct right-hand side given only this information that it has, which is the next token. Okay. That's the essential notion of a predictive parser. So a predictive parser is essentially a top-down parser that does not implement backtracking. That's the same concept. It's essentially deterministic parsing. So the one that does the backtracking is basically able to deal with non-determinism in the building of the proof. So the assumption is that no backtracking is possible, essentially, that you have to, whenever backtracking becomes necessary, that would be the cases where you have ambiguities. So if you want to have predictive parsing, you have to remove ambiguities before you actually do the parsing. You have mainly two different kinds of predictive parsers, either a recursive descent predictive parser or a table-driven predictive parser. So that's essentially the two different avenues that I'm going to allow you to use in your assignment number 2 for the whole project. There are other kinds of parsers, but I force you to use a predictive parser, top-down predictive parser. For the recursive descent predictive parser, what you need to, you're essentially hard coding functions that represent the parsing process of each of the non-terminals that are in your grammar. So for each non-terminal in your grammar, you would write one function whose goal is to essentially implement the parsing of each of the right-hand sides that define this non-terminal. Okay. And because it's predictive, then it would you would actually have for each of the right-hand sides that define this non-terminal in the function that parses this non-terminal, you would have an imbricated if statement. And then each of the if statements in the imbrication would be the implementation of one of the parsing of one of the sentential forms that define the right-hand side of one of the right-hand sides that define this non-terminal. And because it's predictive, then it would be able to choose always one and only one of the right-hand sides. And if it cannot go into any of the right-hand sides, then it would actually be, it would have found a parse error or a syntax error. So eventually the choices that it's going to make are going to be made according to which of the right-hand sides to choose from, would be done using what is called the first and follow sets, which we're going to see a little bit later in this lecture. So each function would eventually call other functions. For example, if one of the right-hand sides that define this non-terminal that it's currently parsing using this function, in the sentential form of this right-hand side, you have another non-terminal, then this function would essentially be calling the function that parses this other non-terminal. And if the sentential form contains terminal symbols, it would basically see if the terminal symbol in the sentential form is the same as the next token. If it is, then it successfully parses this token. I'm going to show that once here, and then later on in the next lecture. I'm going to give you some clear examples about that. So essentially here, what you're doing is that you're using function calls to actually parse the subtrees of the tree that you are building. Eventually, you're going to have functions that are possibly recursively calling each other. Using, in this case, of course, right recursion rather than left recursion. The advantages is that it's easy to implement in the sense that it's easy to see what are the rules in your grammar, and then when you write the code, the grammar actually, the code that you write follows exactly the structure of the grammar that you have. Okay. That's one advantage of using this method or this parsing method. So it's hard-coded, so it's somehow easy for you to input code, hard-coded solutions to specific problems that you may have. Or if you want to build an abstract syntax tree, then you just basically hard-code it inside of the code for each of your functions. However, it's hard to maintain. If you, for example, if you're building your parser, and then now you start testing your parser, and then you realize that something is wrong and that the problem is that your grammar was wrong, then you would have to scrap some of your code. You would have to change the grammar. Because your code is based on the grammar, you may have to scrap some of the code that you wrote that corresponded to this wrong grammar. So that makes this method hard to generate a parser that's hard to maintain, or that requires heavy maintenance. Another solution is use what is called a table-driven predictive parser. So in this case, you have what is called a parsing table. So it looks like somehow like when we had a, for lexical analysis, we had a state transition table. Well, in this case, it's not state-based, but you have some kind of table that looks like a DFA table. So for each, basically you would have a table that you have one column for every token that you have in the language, and one row in this table for every non-terminal that you have in the language. And then the parsing algorithm is peeking into this table, depending what token that it has now in input, would peek in the table and then make a decision according to what the table says, and basically proceed this way. What is a great advantage of this is that the parsing algorithm is the same for every language. The parsing algorithm, what it does is basically it reads the next token and then peeks into the table according to this next token, depending on what non-terminal it was now parsing, peeks into the table, makes a decision, and so on and so forth. Okay. So it uses some kind of stack to actually maintain the state in which it is right now. So the advantage that follows from that is that's easier to maintain. So if you change the grammar, then you just basically have to change the table. Okay, you don't have to change the code. This can be somehow easily manipulated. We'll see how to build a table, of course, and the procedure to generate the table from the grammar can actually be automated. So that's one of the popular ways to actually do parser generators. It's not very popular because it's predictive and it requires that you remove all the ambiguities in the left recursions. We will see that the bottom-up methods are much more popular because they don't require changing much of the grammar. Now, very important concept that is present in any parsing method, or I would say the vast majority of the parsing methods, is the notion of first and follow set. So what is this notion of first and follow set? So as you're parsing a certain non-terminal symbol, a predictive parser needs to know what right-hand side to choose, knowing what is this next token and input. So it's parsing a certain non-terminal, and then this non-terminal is defined by different right-hand sides. So it needs to know, as it's parsing this non-terminal, given that it's looking for a certain token and input, then would make a decision as to which rule to choose that can actually generate a transformation that would start by this token that it's actually has in input. That's how it actually works. Independently of if you're having a recursive descent predictive parser or table-driven parser, it's actually doing exactly the same thing. It looks like it's very different, but it's actually doing exactly the same procedure. We'll come back to that later. So if all the right-hand sides begin with a terminal symbol, then choice is very easy to make. Okay, so you have a certain token X in input, and then you have different right-hand sides. One starts with X, the other starts with Y, and the other starts with A. Of course, you're going to choose the first one because it starts with X. But what if it starts with a non-terminal symbol? How do you determine if that's the choice you want to make? If it starts with a non-terminal symbol, then if you want to choose this avenue, then you must determine what is what is called the first set of this non-terminal symbol, or what if you generate all the sentences that this non-terminal symbol can generate, and the first set is the set of all terminal symbols that can start a sentence that can be generated by this non-terminal symbol. So that's what is the first set. So let's see an example. Here it's going to be very abstract, conceptual. I'm not going to explain how you generate the first and follow sets. This will be in the next lecture. So this is our grammar that we have transformed, remove the left recursions. Okay. Now we want to determine a first set of all the non-terminal symbols. So first of E, first of E prime, first of T, first of T prime, first of F. Let's start with first of F. So if you have an F, what are the terminal symbols that can start any sentential form that F can generate? In this case, it's very easy because F is either 0 or 1 or E between parentheses, which must start by open parentheses. So first of F is 0, 1, open parentheses. Okay, so that's a simple case here. The difficult cases come when you have either one of the right-hand sides starts with a non-terminal symbol, or one of the right-hand sides starts with epsilon. Now let's go arbitrarily first of E. So first of E, so what is it that can start an E? E is defined as TE prime. So whatever starts an E is whatever starts a T. Now what is it that starts a T is whatever starts an F. So what is it that starts an F? We already determined that it's 0, 1, open parentheses. So whatever starts an F is whatever is included in whatever starts a T, which is included in whatever starts an E. So first of E is 0, 1, open parentheses. Now what is first of E prime? First of E prime is, so E, what is it that can start an E prime is E prime is plus DE prime. So whatever starts E prime includes plus. Okay. Now you have here this epsilon. So when you determine the first set, you're allowed to say that first of a non-terminal symbol includes epsilon. This is going to become important in the definition of the follow set. Okay, so and then first of T is what starts at T is whatever starts in F, which we already define as 0, 1, open parentheses. And then first of T prime is star or epsilon. Now, what is follow? The notion of follow is as you are parsing a certain non-terminal symbol, after you've finished parsing this non-terminal symbol, what is it that can be coming? What are the terminal symbols that can be coming after the complete parsing of a non-terminal symbol? So, for example, if you let's take E. In this case, in order to determine the follow set, you have to look at the right-hand sides. So in this particular right-hand side here, basically tells you if I successfully parse an E using this right-hand side, then after this E is close parenthesis. So essentially, follow of E includes close parenthesis. Okay. Now, what is E? E is the starting symbol. So what is it that can come after the starting symbol? So what is it that comes after a sentence? It's essentially the end of the file. Okay. So if you successfully parse a program, then what should be after this program is only one thing, which is the end of the file. If you have a correct program, which is followed by a token, then this token does not belong there. It's an invalid program. So what should follow a valid program is the end of the file. In this case, the convention is to use a $sign to represent end of stream. So follow of E is either close parenthesis or end of file. Now, what about follow of E prime? Now, follow of E prime, so you see that whatever follows E prime, so E prime is actually at the end of what is an E. So what follows, so we know that what follows this E here can be, for example, the end of the file. So by definition, we know now that if $sign can be here, then we thus know that $sign can follow E prime. Okay. So I'm verbalizing this here, but next week we're going to see the formal definition. Okay. So you see that basically you have to analyze the right-hand sides of your grammar in order to determine what is the follow sets. Okay. Determining the follow sets is much more complicated than determining the first sets. And in fact, determining the follow sets is also using the first sets. So all this to say, if you compute the first sets of this grammar and the follow sets of this grammar, then that's the sets you would come up with. And whatever parser that you're building, you need to have the first and follow sets of your grammar, even if it's not a predictive parser. Even top-down or bottom-up parsers, you still need the first and follow sets. Now, if you do your recursive descent predictive parser, then this is how you would use your first set and follow sets. The first and follow sets would be used to help you make a decision as to which of the right-hand sides to use. Okay. Now, for each of, if you build a recursive descent predictive parser, for each of your non-terminal symbols, you have a function plus the parse function, which is the top one. That starts the whole process. So as you parse, basically what you do is you consume next token that allows you to make a decision. Okay, so you successfully, anytime you call next token, you successfully parse the first token. Or you consume this token and you try to determine if it was a valid token. Then what you do is you would when you start, what you want to do is to successfully parse an E, which is your starting symbol. If you successfully parse an E, then you want to successfully parse the end of the program. If you successfully parse an E and the end of the program, then you successfully parse the program. If any of these is false, then there was a syntax error in your program. So you see here that this is pseudocode. Okay, so that's basically assuming that here this means I'm calling another function, and here this is basically checking if the next token I have in input is actually this token here. If it is, then that returns true. And if I sequentially have true, 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 true in this sequence here, which is on my right-hand side, then if I have all true, then this is true. If I have one of them that returns false, then this is false. And basically, that's a syntax error. Now, what is an E? The E is TE prime. So for each of my parsing functions, I would have one alternative for every of my right-hand sides. So for E, I have only one right-hand side. Okay? And for every of the right-hand sides, then I would use my first and follow sets in order to determine if each of which of the alternatives to actually choose. Okay. Now, if I am to choose this alternative, which is the only alternative, then T or the next token I have in input should be in first of T. I'm expecting a certain token, and I'm using this only rule here. If the next token I have in input is not in the first of T, then this token does not belong there. It's a syntax error. Okay. So you see here that in order to make a decision as to which right-hand side I'm going to use, I'm going to use the first set of the first symbol in the right-hand side. Okay. So if my next token is in the first set of TE prime, or the first set of T, then I do parse a T and then an E prime. Okay. If I successfully parse a T and an E prime, then I have successfully applied this rule. And if any of these is false, then this is a parsing error. For E prime, you see that I have two alternatives because there's two right-hand sides. So the first one is this right-hand side here. So you see that this one starts with plus. So it's a little bit more simple, because if my next token I'm parsing an E prime, the next token I have is plus, then I know this is the alternative I want to use. Okay. Essentially, my plus that I'm looking for is in the first set of plus TE prime, which is clearly plus. If my next token is plus, then I match a plus, which clearly is, and then I try to parse a T and then parse an E prime. If all of these are true, then I successfully applied this rule. If any of these is false, then there's a syntax error. Then it's possible that my next token is not plus. So then it should be this case here. Now, what is it that I will use to determine if I should or to choose this alternative would be valid is if the next token I have an input is what follows the E prime, because the E prime is basically not there. So my next token should be what can follow an E prime, because the E prime is not there. So you see, if I want to use this branch here, which is this right-hand side here, then I check if my next token is in the follow of E prime. If it is, then I have successfully applied this rule here, which is E prime gives epsilon. Then for T prime, which is very similar to E prime. So I have either times ft prime or epsilon. So you see that it looks very much like the same here. I'm not going to repeat it. And eventually you have T prime. Oh no, this was T, sorry. T, sorry. T is ft prime, which is mostly the same reasoning as for E, so I'm not going to repeat it either. So essentially T, the only alternative is that it's ft prime. So if I'm parsing a T, then I should be having an input, something which can start an F. If it's not the case, then I have a syntax error. If it is the case, then I should try to parse an F and then a T prime. If I do parse both in sequence an F and a T prime, then I have successfully applied this rule. If any of these turns false, then I found a syntax error. So again, repeat, the T prime is mostly the same as the E prime conceptually, so I'm not going to repeat it. F is one interesting one because in F, all the alternatives all start with a terminal symbol. So each of these branches would actually check if either the next token is in first of 0, then I would actually be using this rule here. If the next token is in first of 1, then I'll be using this rule here. If the next token is in first of E between parentheses, which is clearly open parenthesis, then I would be matching open parenthesis, then parsing an E, and then after that, I would be matching the closed parenthesis. Note that here, when I call E, that would be starting the whole thing all over again. That's why it's called a recursive descent predictive parser. Very often, or most programming languages would have recursive rules when you have lists, among other things. You see, this is how the recursive descent predictive parser is organized. Okay, so this is a pseudocode, of course. Depending on what programming language you want to use, you're going to have some things to to figure out in the particular programming language you're using. So that's it for that. I did not explain here how to do the table-driven predictive parser. That's what I'm going to do in the next lecture. So we're going to see that it's in fact doing exactly the same procedure as what the recursive descent predictive parser is doing. It's going to be using the first set and follow set and so on. It's going to use a stack to actually maintain the state in which it is, or what non-terminal symbol it's currently parsing. So you see that this parser here, when you're currently parsing an E prime, you are in this method here, or this function here. That's how it knows which non-terminal it is currently parsing. Well, the table-driven parser is going to use a stack to actually push these non-terminals onto the stack to remember what it was currently parsing in order to make a decision depending on what next token and the parsing table that it's using that represents the grammar. So that's it for this video. Thank you.